In this next installment, we're going to start with CIPSR, the Theory of Computation, which is, I think, the best introductory book to computational theory and complexity theory. So it does things like automata, it does things like regular languages, automata, context-free languages, it does Church-Turing thesis, does Turing machines, decidability, reducibility, a Turing reducibility. Then it goes into time complexity, the P class, the NP class, P versus NP problem, space complexity, intractability, and advanced topics like parallel computation, cryptography. If you're into computation theory, this is very much the book that you want to start with. It's a very nicely written book, nice to read, easy to read. It's very, yeah, it's perfect. Very nice book. Then we have a chemistry book by Macquarie. Here is Macquarie's chemistry book. Macquarie also has a physical chemistry book, but this is the general chemistry book, which is like introductory chemistry. And I like this a lot because it does atoms first. It doesn't do atoms mathematically, but it's goes bottom to top. So it starts with quantum theory, ionic bonds, Lewis formulas, molecular geometries, covalent bonding, chemical calculations, gases, kinetics, acids and bases. So this is really an entire full course on chemistry, basically. Very nice book, very not too dumbed down. Most introductory chemistry books are really dumbed down. But this one isn't. This is very nicely written. Then another book, chemistry book, which is a bit more dumbed down, is Fundamentals of General Organic and Biological Chemistry, which deals with both chemistry. So we see atoms, we see ionic compounds, molecular compounds, chemical reactions, mole and mass relationship, chemical reactions, gases, liquids, solids, solutions, acids and bases, nuclear chemistry, organic chemistry, alkenes, compounds with oxygen, aldehydes, amines. Then we go to carboxylic acids, amino acids, enzymes, carbohydrates, biochemical energy, carbohydrate metabolism, lipids, lipid metabolism, proteins and amino acid metabolism, nucleic acids, genomics, chemical messengers, and body fluids. So this starts from basically from scratch, from chemistry, and it goes all the way to really biology and biochemistry. So it does all of that really, really comprehensively, but not in depth at all. Here's a really nice book on fluid mechanics, physics of continuous matter. This one is not for engineers, it's for physicists. So it starts with fluids at rest, buoyancy, hydrostatic shapes, surface tension. Then it goes to fluids, solids at rest, where it does stress and strain, Hooke's law, electrostatics, elastostatics, fluids in motion with continuum dynamics. We have ideal flow, compressible flow, viscosity, channels and pipes, rotating fluids, computational fluid dynamics, balance and conservation, entropy, energy, elastic vibration, gravity waves, boundary layers, subsonic flight, convection, turbulence. So yeah, this is a very in-depth book on all kinds of solids and fluids in motion and at rest. It is very nice, very in-depth, very physically motivated. Also quite some math is needed in order to appreciate it, but I guess it's normal. The next one is one of my favorite books on quantum mechanics. You see the book by Merzbacher, Quantum Mechanics, and it deals, just an ordinary quantum mechanics book. So it deals with wave mechanics, Schrödinger equation, linear harmonic oscillator. It also has the spin, rotation, perturbation theory. It has scattering, it has identical particles, many body systems, and then finally it ends with photons and relativistic electron theory. So the book is nice. It is somewhat more advanced physically and mathematically. It does not seem to use the stupid bracket notation, which I don't really like. I never really liked it. And it has inline exercise in the text, so it is a very neat book, very fun to read. Next comes the best book on special relativity from mathematical point of view by Neighbor, The Geometry of Minkowski Spacetime. So here's what it covers. The book starts with geometric construction on M, and it starts by deriving everything mathematically rigorous. So this is completely mathematically rigorous. Linear transformation, electromagnetic fields, theory of spinors, topologies for M, spinorial objects. So this is a very rigorous mathematics book that still deals with physics. So it's basically physics for mathematicians. But yeah, it's all there. It's all there. All of special relativity is here in a very rigorous perspective. My favorite optics book is next. Is Jenkins and White, Fundamentals of Optics. Very neat. You see we have here properties of light, speed of light is figured out. Plane surfaces, prisms, spherical surfaces, thin lenses, thick lenses, spherical mirrors, ray tracing. What else do we see? Optical instruments. Then we go to wave optics, vibration and waves. We have a superposition of waves. We have multiple reflections. We have Fraunhofer diffraction, double slit, diffraction grating, Fresnel diffraction, the speed of light methods, electromagnetic character of light, sources of light, absorption, scattering, dispersion, polarization, reflection, double refraction, interference, modern wave optics, quantum optics, light quanta, lasers, holography, magneto-optics, dual nature of light. So yeah, that's really a lot of optics, basically all of optics that you need to know in a very nice book. Very nice book. It really starts geometrically. It really starts with ancient optics, but it goes very modern into quantum mechanics optics. Another one of Cox's books, Galois theory this time. So this is my favorite book on Galois theory. Very neat. It does the cubic equation, then it goes to symmetric polynomials, roots of polynomials. It has extension fields, normal and separable extensions, Galois group, the Galois correspondence. It has solvability by radicals, cyclotomic extensions. We have geometric constructions, finite fields. We have Lagrange, Galois, and Kronecker, computing Galois groups, solvable permutation groups, and then appendices on abstract algebra. So yeah, there's a lot of very neat applications. Also very historically motivated, even though it's not a historical book. It doesn't go to the historical questions, but it does tell you a bit how everything came to be and how everything started. Here is Holland's analysis book. It's not really an analysis book. It doesn't really do epsilon delta proofs or anything. But it's basically, yeah, the methods of analysis for physicists. So it starts with differential equations, first and second order. It goes to Hilbert space, linear second order differential equations in L2 spaces, Schrödinger equation, the Bessel operator, eigenvalue of the Laplacian, and then we see here the Fourier transform. So yeah, neat book. It does a lot of fun stuff. Very little proofs though, so it's all, but it does have very nice intuitive explanations. Here you have Bressot's book on multivariate analysis. You see here the Newton's second law, the Stokes theorem, and the Einstein relation, the wrong one. This is a historically motivated multivariable book, and it does all the topics you would expect. It starts with the orbits are ellipses, the discovery by Kepler, the vector algebra, celestial mechanics, differential forms, line integrals, linear transformations, differential calculus, integration by pullback, differential calculus, fundamental theorem of calculus, and then it ends with ESMC squared. So historically motivated, a lot of history behind it, a lot of reasons why everything should exist, but also quite rigorous and quite fun exercises. I think I like this book a lot. One of Singer's books, Stephanie Singer's books on the hydrogen atom. Yeah, an entire book on the hydrogen atom and the mathematical theory behind it. So it has setting the stage, linear algebra of the complex numbers. It has Hilbert space, Lie groups. It has representation theory, reducible representation theory. Then it has the algebra SO4, the group SO4, projective representations. So yeah, it has a lot of neat stuff just on hydrogen atom. So it really explains all of these advanced methods, advanced algebraic and analytic methods, all on the hydrogen atom in order to make it intuitive. Then here we have Cheng, field and wave electromagnetics. So it is just an electrodynamics book, but one that is very rigorous mathematically. Static electric fields, electrostatic problems, steady electric currents, steady magnetic fields. Then we have time varying fields and Maxwell equations, electromagnetic waves, theory and application of transmission lines. There's waveguides and cavity resonators, antennas, and then a very thick book on electrodynamics from a mathematical rigorous perspective. Definitely a gem of a book, but if you're into physics, maybe you won't like that one too much. Here we see the newest book of Moore, his book on the standard model, which is I'm working through right now. Another gem. It's another workbook, so he has a lot of exercises, very minimal theory, and it's this Klein-Gordon equation, Noether's theorem, quantum mechanics, angular momentum, annihilator operators. It has quantized scalar fields, the toy universes, the Dirac equation. It has a lot of standard model stuff. It's all for undergrads, so his explanations are pretty good, but they can't be like the most advanced explanations, and you can't really use much in-depth math because people don't know that at that point. But it's a very written book. Highly recommended, of course.